All right, welcome to week 14, day one. We're going to do a 15-minute talk on matrix math. So everything you do in a 3D video game takes place in a 4x4 matrix. And so it looks something like this. Let's see if I can draw it straight, actually. There we go. Just reinstalled the drivers for my tablet. So this 4x4 matrix is used everywhere in 3D graphics. So if you look at like Intel CPUs, they accelerate 4x4 matrix operations. The reason for that is because when you do 3D graphics, everything takes place inside of a 4x4 matrix. And so the way these things look is if I don't draw something in there, it's a 0. Okay, so this thing here is called the identity matrix. And so if you multiply something by the identity matrix, you get the original thing back out. This is the matrix equivalent of times 1. Okay, so this is kind of like your go-to thing when you do matrix math. The way that matrices work is that they embed the three main operations you guys do in 3D worlds, right? Which is rotation. You guys know what the other two are? So inside of Unreal Engine, you can hit a key and then you can move something around. What is that called? There's WR, movement. Yeah. Do you know what the technical term is for it? Translation. Very good. Translation means moving things around. You have a box, you can move it southwest, east, north. Rotation means you can take the box and then rotate it like this, right? And then what's the third thing? Scaling. Yeah. Rotation, translation, and scaling. So you have a small box and you make a big box or a rectangle. It doesn't have to be uniform scaling, or you can make an itty bitty tiny little box. And so these three are the basic operations that you do inside of like basically any 3D thing, right? Like Ramirez, you've worked in Blender, right? You've seen rotation, translation, and scaling in Blender, right? It's not just in Unreal Engine, right? Yeah, yeah. So it's everywhere. Okay, and these things get all encoded into a single 4x4 matrix. So you don't actually have to do a separate rotation operation, a separate translation operation, a separate scaling operation. All of them take place inside of one 4x4 matrix, and I'm going to explain that to you right now. So the way that it works, the way that you do these things is that this is called a transformation matrix. Okay, 4x4 transformation matrix. And so there's actually no additional cost to doing translation and rotation versus just translation, let's say. What you have is you will have a point in, let's say, local space, right? So if you have a rocket ship here, and the rocket ship is, pointed off to the right here, and let's say that's the origin of it, right? You've seen the little white dot when you're working with a model, right? That's the origin of the model, and it's like the dinosaur in world space. It's 0, 0, 0. So this spot here at the very end of the rocket ship, this spot here might be like I don't know, 10 centimeters to the east, right? So it might be 10 east, 0 up, and 0 in the z direction. So you're going to write it like this: X, Y, Z, and then the bottom number is always 1. Okay? Now let's say that you wanted to pipe this through the transformation matrix, and you wanted to scale the rocket up twice as big. Well, scaling always takes place around the origin, right? And so like if this point here was like 5 away, after you scale it up, it'll be 10 away. And this point here was 10 away, after you scale it up by a factor of 2, it'll be 20 away. Do you guys understand? Like everything grows outwards from the origin. So when you scale something, if something was 100 away before and you double the scale, it's now 200 away from the origin. Does that make sense to you guys? Like it kind of grows outwards in all directions when you do a scaling. That the center point is the place where it'll zoom out from. You guys with me? So what we want to know is where the tip of the rocket ship will be after you've scaled it by a factor of 2. You guys with me on this? It's dead silence on Discord. It's like if you have a box, and if the center point is here, when you scale it, it's going to scale like that. Like it's going to grow up and right. Whereas if the center point was here, then it's going to grow outwards in all directions like that. Okay. So you've got a point here in a local space, 10, 0, 0, and you want to know where it will be after you double it. So this here is a transformation matrix for doubling the scale of an object. So 2, 2, 2, 2 is the scale, twice what it was before. So how do you do this? How do you do a matrix? This here is a matrix. This here is a vector. You're going to multiply them together. How do you do that? Well, what you do is you take the vector and you turn it sideways. So you take this, you turn it sideways, and you end up with 10, 0, 0, 1. You multiply down, and then you add across. So all the blanks are zeros, so I'm not going to bother writing them. So what is 10 times 2? Everyone, what is 10 times 2? Taking it back old school. Hmm, 20. Yeah. So 10 times 2 is 20, and so the answer here is 20. 0 times 2 is 0. 0 times 2 is 0, so it's 0 and 0. 1 times 1 is 1, and so that is our answer. This is the x value, this is the y value, and this is the z value. Okay. And same thing for the results. Okay. So what we had was a rocket ship. The point of the rocket ship, the tip of the rocket ship, was 10, 0, 0 before, and now it is at location 20, 0, 0, because we did a times 2 scaling. Okay. Now, what if we don't just want to double, and if we do this for every point on the rocket ship, like let's say we had a point here, like let me draw in a different color. Let's say we have a point here, and this point is like, I don't know, 3 east and 2 north. So it's like 3, 2, 0. It's a terrible parentheses. 3, 2, 0. Then if we repeat this process here, 3, 2, 0. When we take, this is the point, this is the location, x, y, z, 3, 2, 0. If we repeat this process of multiplying down and adding across, 3, 2, 0, 1. 3 times 2 is what? 6. Plus 0 plus 0 plus 0 is 6. 2 times 2 is what? 4. Times plus 0 plus 0 plus 0 is 4. 0 times 2 is 0. It's all zeros there. And then we got a 1 here. And so this is our final location. So if we had 0.320 before and we doubled its scale, it will now be at 0.640 afterwards. It is now doubled in size. And so every point on the rocket ship goes through this transformation matrix to get the final point. And the points are like the edges of the triangles, right? So the tips, it's like if you have a triangle, every point, on it goes through that transformation matrix to find out where it is at the end of the day. And then that'll get filled in with color by like a fill algorithm or something like that, or materials will come in, shaders will run, things like that. But basically, every point, every vertex in a triangle goes through the transformation matrix, and it scales everything out by 2. So now let's say we want to translate it. Let's say we want the rocket ship not only to double in size, but we also want it to move upwards. We want it to move up 10 units in the y direction. So these 3 numbers here are the scale. So if you don't want to scale it, 1, 1, 1 is the numbers. These 3 numbers here are the translation. So this is the translation in the x direction, translation in the y direction, translation in the z direction. So if we want to both Scale the rocket ship by a factor of 2, make it twice as big, and move it 10 up in the y direction. What we put in here is 0, 10, 0. Okay? Again, blanks I'm leaving as 0 because I don't want to write like 50 million zeros. Okay? But it's like, these are all zeros, right? Okay, so if we do this again, our transformation matrix now means both double in size and move 10 up in the y direction. So if we do the math again, 3 times 2 is what? Everybody? 6 again. Cool. 6 plus 0 plus 0 plus 0 is 6. 2 times 2 is 4. 4 plus 0 plus 0 plus 10 is what? So you multiply down and then you add across. So 2 times 2 is 4. 1 times 10 is 10. 4 plus 10 is what? What's our answer? 14. Very good. So that. 0 times 2 is 0. These are all zeros still. Get a 0. 1 times 1 is 1. Boom. And so now, instead of ending up at 3, 2, 6, 4, 0, so instead of that point becoming 6, 4, 0, it's going to move north by 10 and end up at 6 to the east, 14 north, and 0 in. So this transformation matrix both doubled the size of the spaceship. The spaceship is going to go from like this big to like, I don't know, twice as big. It's like twice as big now. And it's also going to translate upwards by 10 units. So the thing is going to move up here. So it doubles in size and moves north by 10. All right, and then the last thing that we can do with a translation matrix is to rotate it. And so rotation transformation matrix 3D version of it. And so you can rotate around 3 different axes. You can rotate around the x-axis, which will rotate it into the screen from our perspective here. You can rotate it around the y-axis, which will rotate it like this towards the camera. Or you can rotate it around the z-axis. The z-axis is going into the screen right now, which will cause it to rotate on the screen. So we want this one. So if we want to rotate it 90 degrees, then we're going to use this equation right here. Okay. So copy image, paste our little cheat sheet down here. Take a look at it. Okay, and so we are going to shoot. That's 2-dimensional. Oh no, it's fine. Okay, so we are going to change this. What is the cosine of 90 degrees? You guys remember trig? Zero. What is the negative sine of 90 degrees? -1. So we're doing this one here, right? Doing that equation there. What is the sine of 90 degrees? 1. And what is the cosine of 90 degrees? 0. So that is the transformation matrix to rotate something 90 degrees. Okay? And I don't remember if it's clockwise or counterclockwise. If you want to scale it still, then, and that's a 1 still. If you want to scale it, then we would turn all these 1s into 2s. So we can do that just to show you the final product before we finish for the day. And so here we have a matrix that will rotate the points in the spaceship by 90 degrees. It will double in size, and it will be moved northwards 10. So if we do the math one last time, bloop, bloop, bloop. Our input point is still 320, so this point here. 3 times 0 is 0. 2 times -2 is -4. -4 plus 0 plus 0 plus 0. And again, I'll just leave these as blanks so we don't clutter up the screen. So, not there anymore. And we can get rid of view as well. Okay, so 3 times 2 is 6. 6 plus 10 is 16. 2 times -2 plus a bunch of zeros is -4. 0 times 2 is 0, adding a bunch of zeros together, and there you go. So instead of being at 6, 14, 0, we end up having, and this is our XY axis right here. Instead, we end up at -4 in the X direction and 16 in the Y direction. So this thing is actually going to rotate around that way. Yep. If we did it again, it would rotate another 90 degrees and then another 90 degrees and then back to start here. So every time you apply this transformation here, it rotates 90 degrees, doubles in size, and moves north by 10. So that is that. That is what's going on under the hood every time you do something in Unreal Engine and you say, like, get transformation, or if you get world location, or if you get get rotation, things like that. What it's doing is every object in the world has a transformation matrix. It's got it's presented not like this. It's presented in a more human readable format. But under the hood, it's being held in something like this, or maybe a quaternion or something like that. And so the interface makes it really nice to you. You just click and drag and rotate things 90 degrees. But what's happening is you've got some trigonometry going on into a transformation matrix under the hood, and it's just presented to you in such a way that it makes sense. But the good news is, like I said, you don't have to worry, like, all right, I'm doing a translation and a rotation, both. It doesn't matter. Like this 4x4 matrix contains all the information you need to do translation and rotation and scaling for every point on a model. And that is, there's no additional cost to that. Literally every object in the world will go through that. And you don't have to worry about that from a performance standpoint. So for example, if we click on this wall here, you can see, look, here's the location, here's the rotation, and here's the scale. Okay, so this is like I said, like these three numbers here, it's just pulling them out of these three numbers here. The rotation and scale are these 9 numbers here. These are all zeros, these are always ones, these are always ones. Okay, so it is just a very light coat of paint on that mathematical concept. And every time you rotate something, you'd be like, oh, rotate 90 degrees. And it's just changing that transformation matrix under the hood. So, yeah, that's really what's going on when you got a 3D game. All right. And it's they make it a little nicer to look at than that, but that's really all that's happening. Every point in the world goes through a transformation matrix and ends up with a point in the world. And then when you draw it to the screen, to the camera has another transformation matrix that projects the world onto a screen. Like it's got a virtual screen here, and then all the objects in the world get projected on it, and you handle who's in front, who's behind, that kind of stuff. Solids of revolutions. Oh yeah, like the conic sections and things like that. Or you have a cone and you cut it this way, you get a parabola, and you cut it that way, and no, it's simpler than that. These are all linear operations. And so all the transformation matrices can be stacked on top of each other. So if you've got, for example, an arm, right? And this is how skeletons work. If you've got an arm, let's take this as the origin, the shoulder, just because I don't want to go through all the bones. This joint here is translated a certain amount, and it's rotated a certain amount. It's not scaled really. Scale of all this will just be 1. This is translations and rotations, right? And then that gives you this joint here. And then all of the children of that joint get transformed out by the length of my, was that the humerus? No, what is that? It's radius, ulna. Is that the humerus? Humerus is right. Okay, good. So what are the length of the humeruses? Right, my hand gets moved by that. And everything below my shoulder is getting translated by the length of the humerus and the rotation of the shoulder joint. And then the elbow here has another length of the radius and ulna, and it also has an angle. And so all the children of that get that matrix. And so all these matrices actually just get multiplied on top of each other and get multiplied on top of each other and multiplied on top of each other. And so there's actually a stack of matrices as you go down the line of the skeleton. All of the the transformation matrix for the elbow is just rotate this much, rotate 90 degrees, let's say, and translate this far. Okay. And then the wrist says rotate 20 degrees and translate out this far. And then the middle finger says, rotate this far, and then this joint, and then this joint, and then this joint. And then it goes all the way down, and now it knows where the tip of my finger is. And then after it draws that, then it pops off the stack, and it pops off the stack, and it comes down here. Then it goes down the next finger, pops off the stack, goes down here, pops off the stack, goes down here. It has, and all these matrices just multiply on top of each other. And so then it draws all the hand, then it pops off, then it pops off, then it pops off, then it goes and it does the other shoulder because it just came from the neck and things like that. And so in order to draw all the pieces of a skeletal mesh, it starts at your root, which is the bottom of your spine. And then all the transformations, like when you lean back, when you lean forward, like, do you guys understand what I'm saying? Like if I just rotate from my waist, my hands, my head, everything follows that, right? Everything moves with the root. Okay. And if I just bend my head forward though, these fingers and stuff are not children of the head, right? So I can move my head up and down and it doesn't move these things because I'm not multiplying the transformation of my neck. Whatever the rotation of the neck is, don't get multiplied on this because they're not children of the neck. Okay. And that's all animations are really, is you just program in at time 0, my finger is here. At time 5 seconds, my finger is here. And so it'll just, you'll do a lerp, a linear interpolation, or some other cubic interpolation or something, and then when you animate it, it just goes, and that's it. So you just program in different keyframes, right? Here's time 0, here's time 5. So over 5 seconds, 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, right? It'll move down. And so that joint is the only thing moving. And none of the other joints have any animation, data attached to them because they're not doing anything. And so that's one of the reasons why if you have a skeleton that has additional bones, it actually doesn't break anything. Because let's say that you add a bone for like wings, right? So like you're a human like me, except you got wings, right? If you retarget the animation with a standard human skeleton, which I'm a standard human, right? I don't have wings actually. Those wings won't animate. Why? Because you're doing like the polka animation or the running animation or the sidestepping animation. It has motion for all of those bones. Start here at time 0, start here at time 5, start here, but it doesn't have any information for the wings. So the wings just sit there. They're just going to be like this. They're not going to animate. You're going to run around. The wings are going to be like this, and they're not going to animate, and it's fine. But if you have specific animations for that skeleton, then you can have flapping animations and things like that. But in general, animations are actually pretty robust. Pretty much any bipedal, humanoid kind of thing, alien, whatever, you can basically share the same animations, even if you've got some extra bones. Like you got, I don't know, like maybe some aliens can like control their ears and have their ears wag and things like that. If you just don't provide animation information for them, they just don't animate. It's not a big deal. So they're gonna. Yes, I too am a human. This is Zuckerberg. Greetings, fellow humans. Clothes, yeah. So clothing and fabric is like another lecture. There's actually some really neat fabric stuff you can do in Unreal Engine. They have like an entire fabric engine on getting that to work, and some of it is kind of like trial and error getting it to work. But that's a different lecture. Clothes, backpacks, things like that. Those are usually attachment points on the skeleton. So like hats, for example, you make an attachment point for the top of the head. And then when you have a static mesh for a hat, but it doesn't have to be a hat. It could be a canapé. And you say attach the canapé to the socket. Now you've got, as the person runs around, there's a canapé on their head. And wherever the head animates, the socket follows the head, and the canapé will just sit there on top no matter what you do. The only tricky part with hats is hair. So have you guys ever played a game where like you put on a hat and like the hair vanishes and like the person's bald? Like you put on like a crown or something and then like the hair just goes away. The reason for that is because oftentimes they turn off hair if you've got like a full helm on or something like that, because you don't want the hair sticking out through the hat, you know? So yeah, hair is actually one of those really annoying things to get right, because if you just turn off the hair and the hat shows some of the hair, then you see the person's hair vanish, which looks bad. But if you have like a giant afro or something, you put like like a full helm on, you don't want the hair sticking out through the helmet. So it's actually one of those tricky things where like you might actually have you cut the hair short or something like that. So it's like if you have like a headband on, like it works fine, but like if you have a helmet, like it cuts the hair to a certain, like it's tricky. So new hair mesh, yeah, like it's just kind of one of those things where a lot of games have bugs related to hair. Especially in games where you have DLC hats and things like that. For whatever reason, hats are like the thing, and hats are like the worst thing from like a game development standpoint. Like to get right, because hair is such a pain to deal with, and so everyone's like more hats. It's like, no, do gloves, do DLC gloves. That's easy. I'll have branded named gloves. I don't know, or give me nose rings or something, like that's fine, because nose rings don't cause your nose to vanish and things like that, but hats are like the worst. So okay, so that is our lecture for today. Thank you all for coming out. Your homework is to find 3 assets that are from a source that you've never used before and add them to your project. Easy peasy. Okay, so thanks everyone, and I appreciate you guys all hanging out for the full duration today. I'll see you guys next time. Peace out.